Hello everyone, welcome to a new video series on electromagnetic fields. In today's video, we are going to discuss about a new unit which is electromagnetic waves. So to start off with, we will discuss in this video about wave equations. So this is the agenda which we are going to follow in this video. So first we have going to look about an analogy for wave equation through a water ripple analogy, and then we are going to derive the wave equation from Maxwell's equation, and then we'll deep dive into the wave behavior with concept discussion, and then we are going to connect the wave equations, wave parameters with real world applications, and finally we are going to end up with a short recap of few quiz questions. First, let's begin with a wave ripple analogy. In order to identify or to understand the nature of waves, this analogy helps very much. Imagine dropping a pebble into a pond which is very still and calm. When we drop the pebble into the pond, we could observe concentric ripples spreading out beautifully, which illustrates the wave propagation. Just like how the wave propagates in the form of concentric waves in the water, the electromagnetic waves will also propagate in the same manner. It carries energy, it carries momentum without the net transfer of matter. So these propagate in space with the help of electric and magnetic fields. So with this analogy, we can easily visualize how waves will propagate in real life, which are invisible, and we can also imagine the wave characteristics like wavelength, frequency, amplitude, etc. So next, let's derive wave equation from Maxwell equation. Wave equation consists of two parts. One is electric field and the other one is magnetic field. Together we have electromagnetic wave. So it comprises of two parts, electric field part and the magnetic field part. So to get this electric field part, we take the Maxwell's equation, which is modified from Ampere's law as the base equation, and for magnetic field we use Faraday's law of induction with a modified version of Maxwell's. These two equations will be the bedrock equation for this wave equation derivation. Then for these equations we are going to take curl for both Ampere and Faraday's law, and then we are going to utilize these equations again by taking another curl in order to get the wave equation. So the general wave equation is given by del square E is equal to mu epsilon dou square E by dou t square. So this partial derivation equation will derive how the electric field propagates in source-free, isotropic and homogeneous medium. A similar equation for magnetic field will also be derived, which is given by del square H is equal to mu epsilon dou square H by dou t square. A simple replication of this wave equation for electric field into magnetic field can be easily done. So for magnetic field, the E can be replaced by H, which is magnetic field intensity. Here E is the electric field intensity. So here the del square is the Laplacian operator representing the spatial variations of field, and also since it consists of both electric and magnetic field, we include the measure of the magnetic material and also the ability to produce electric field, which is permittivity. So both permittivity and permeability is included in this wave equation. Now let's observe this wave behavior in different mediums. We have different mediums like vacuum, dielectric materials and conducting mediums. Let's observe how this wave equation is reflected in each medium. In vacuum, the permeability becomes mu naught, because you cannot have relative permeability for vacuum. So therefore permeability for free space is available, and also epsilon becomes epsilon naught, which is permittivity of free space. Therefore the wave speed simply c is equal to 1 by root of mu naught into epsilon naught, which is the speed of light. So in vacuum, the wave travels with the speed of light. In dielectric medium, the mu and epsilon changes because at every dielectric medium will have its own relative permeability and permittivity, which is mu r and epsilon r, which are affecting the wave speed and wavelength. So that is why when light slows down when it enters the waters or glass, leading to phenomena like refractions. So that is why we can observe this property called refraction in dielectric materials, because there is a change in wavelength and wave speed with materials. For conducting medium, the wave experience attenuation due to current flow. So therefore, these wave equation becomes even more complex, including the terms like conductivity and also the damping of the fields. Now let's look at the applications of electromagnetic waves. Whatever we see around us is an application of electromagnetic waves. In basics, here we have listed few for our deeper understanding. We have electromagnetic waves applications in lights and optics, radio communication, medical imaging like X-rays, and then microwaves and radars. So for light and optics, from fiber optics to laser, the wave nature of light can enable us to precise control and manipulation for communication and imaging, because the fiber optic communication is completely electromagnetic wave applications. And for radio communications also, a form of electromagnetic radiations are essential for broadcasting those radio waves through wireless internets, mobile communications, for longer distance communications. For X-rays, high energy and short wavelength electromagnetic waves are used to penetrate through soft tissues in order to get the valuable data from human body. Therefore, we can easily diagnose the images of bones and internal structures, tissues, etc. In microwaves and radars, microwaves are used in ovens for heating, and in radar systems we use microwaves for detecting objects, measuring their distance and speed. So ultrasound waves are used in order to forecast weather forecasting and also for air traffic control. So far we have discussed about what is electromagnetic waves with a wave analogy, and then we discussed about the wave equation from Maxwell's basic equations, which are derived from Ampere's law and Faraday's law, and we have seen wave equation for electric field and wave equation for magnetic field, and then we see about how this wave nature in different mediums like vacuum, dielectric materials, and then conductors, and finally we listed few applications of electromagnetic waves. Finally, these are the key takeaways we discussed so far. For further understandings, you can have a look into these books, which gives a deeper understanding about electromagnetic waves, and also you can go and visit tutorial points like electronic tutorials where you can visualize the electromagnetic waves, and we can also get materials in MIT open courseware in electromagnetics. So with this we come to the end of this video. Thank you. Thanks for listening. In the next video we will discuss deeper about electromagnetic waves. Thank you. Thanks for listening.